Today I got a pretty easy approachable problem for you guys. Problem 2506, count pairs of similar strings. This is a recently released problem in the most recent competitive programming competition batch. So hopefully this is an opportunity for a new solution you haven't seen before. And I posted prior to other people approach this problem and post their solutions online. Anyways, let's go. Okay, so count pairs of similar strings. You're given a zero index string array words. Two strings are similar if they consist of the same characters. Okay, so ABCA and CBA are similar since they only contain the characters A, B, and C. Right? So regardless of the number of times a character is seen, we just want to look at like the set, right? The number of letters that were used, the number of unique letters used to create that word. However, ABACBA and BCFD, they're not similar, right? Because this is created with A, B's, and C's, and this is created with B, C's, F's, and D's. So they're only the same if they use the same unique letters, exactly the same unique letters. Return the number of pairs such that 0 is less than equal to I, less than equal to J. So word, so return the number of pairs of words that are similar. Okay, so the easiest solution here would be to just look at each pair, so n squared pairs, right? Look at each pair and then create a set from both of them and see if they're the same set, right? Because the set will take each letter and find each unique letter. So take each word, look at the sets that create each word. If they're the same set, then that's an additional pair, and then you can return that. But there's actually a more efficient solution. So if we were to hash these words based on the number of letters, what's a way that we could do that efficiently? Well, the word only consists of English lowercase letters. So if we were to create a string, like if we had AABC and ABC, what could we map this to in order to say like this is the same thing as another thing, right? This and this are the same. What could we map this to and map this to so that they're the same thing? Well, if there's an A, we'll put a 1 in that slot. Since there's a B, we'll put a 1 in that slot. And since there's a C, we'll put a 1 in that slot. And then we'll put zeros in the rest of the slots. Because there's 26 letters in total. So if we put 26 zeros here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Maybe there's not 26 here, but you get the point. So for AABC, so since there's an A, there's one unique A, there's one unique B, there's one unique C, and then maybe there's an E in here. So there's an A, there's a B, there's a C, there's no D, and there's an E. So this would be the associated string, or the associated number. ABC, well, there's the same thing, but there's no E. So this would be instead of 0, right? And then we could compare these and just say, okay, if these are the same, then the number is the same, right? The uniqueness is the same. Versus if we added an E to this, although they're not identical strings, we're just trying to keep a count of the count of each thing, right? So this would be a 1, and then we'd say, okay, these things are equivalent. So then we could add that to counts. We could say, okay, the counts of this unique number, which could be anything, right? But using these unique letters, we'd add 1 to that. So maybe we should make this a default dict with the default value of 0. So if we mapped each of these letter strings to this number sequence where it's a 1 if that letter exists and it's a 0 otherwise, we could get each string's unique number, and then we'll know exactly how many strings. So if, well, let's just start there, right? So we'll look at each word. And then we'll say count equals 0. And then we'll look for each letter in the word. And we'll say, okay, well, the count equals the count. We're going to XOR it with the order of the letter minus, we're going to shift the 1 over, the order of the letter minus the order of A. Does that make sense? So that'll shift it over. So if it's A, then we'll make the first bit a 1. If it's C, we'll make the third bit a 1, right? And that'll give us a unique string, right? Because if we have multiple 1s, like if we have multiple A's, it'll just create a 1 there, right? So independent of how many A's, as long as there's at least one A, then that corresponding bit will be a 1. If there's 0 A's, then it'll be a 0. If there's more than 1 A's, there'll still just be a 1 there. So you can get that unique string that way. All right, and then just so that you can see, let's print the bin of C. Let's print the word and then the bin of C. That way you can see this mapping in real time. Right. It's going to fail, but so ABA is just 1, 1. AAAB is 1, 1. So, right, because these are the same, right? Because they use the same 2 letters. ABCD is its own thing, right? Because it uses 4 letters. So this means that the A is a 1, right? BAC, it's its own thing. AABC is the same as this BAC, which is different than these ones, right? So for each of those things, we said, okay, well, the counts of that letter, of that unique binary string, which represents the unique string itself, right? We add 1 to it. What would that mean at the end? So if we print counts, okay, so we print counts here. We notice we have 2 that are this unique. We have 1 that's this unique and 2 that are this unique. Let's change the example and let's add an additional string here just so you can see AABA. So now we'll have 3 of the same kind, right? So now we have 3 that are of the same kind, we have 1 that are the same kind, and 2 of the same kind. Well, if we have 3, that means that any 2 of them could be pairs together, right? Like if I have 3 strings, because in this example, there are 3 strings that are the same, right? These 3 here. There's ABA and AABA and AABB, right? These 3 strings are of the same uniqueness. So these could all be pairs. So how many pairs could I make here? Well, I could match ABA with AABA. I could match ABA with AAB, or I could match this with this, right? So there's 1 pair, 2 pairs, 3 pairs that I could do. The mathematical formula for that is 3 choose 2, right? If I have 3 things here, how many ways can I choose 2 of them? Because that'll be the number of pairs that I can create from the 3. And generally that'd be n choose 2, where n is the length of the number of values, right, that you can create. Oh, it's going to give me an error code. Whatever. Right, the number of values you can create, which would be 3 in this example. So n choose 2, the general formula would be n factorial divided by n factorial divided by n minus 2 factorial times 2 factorial. And then n factorial is really just n times n minus 1 times n minus 2 factorial. I'm just doing the math here. Divided by n minus 2 factorial times, this is all it's supposed to be, times 2 factorial. 2 times 1 is just 2, so just times 2. These things cancel out, so you end up just getting n times n minus 1 divided by 2. So that's what the formula for n choose 2 is. So for each count, if I just do this formula and sum it up, that'll give me the number of unique pairs. Right. So I'll just return then. Well, we'll run it one more time so you can see. What? It's crazy how sometimes, okay, oh, I didn't print it, that's why. So print counts, just so you can see it one more time, so you can see what I'm talking about here. Right, so 3 occurs 3 times, 15 occurs 1 time, 7 occurs 2 times. So there's 2 ways to create this pair, there's 0 ways to create this pair, and there's 3 ways to create this pair, so that'll give you a total of 5 different pairs that you can create. So what we have to do is just return the sum. So we do that formula, n divided by, or n times n minus 1 divided by 2 for n in counts. Remember, the values are the number of elements that have the same uniqueness. So that's the number of pairs you want to find. Counts dot values. And we just return that sum. Okay, and then we submit that and we pray. So there you go. So what's the runtime? And so I've looked at other solutions. No one I've seen has done this one. They do n squared, and then you have to look at each word. So let's say that m equals the length of a word, the longest word, right? So all words lengths are less than or equal to m. And then n is the number of words, the length of words. Right, so m is the length of the longest word, and n is the length of all the words that you have to process. So for time, we have to look at each word once. And so that's going to take n time. So each word, we have to look at all n words. But then we have to also process finding this binary string to find the uniqueness of that word. So that's going to take n times m time. And at the end, we just return the sum, looking at all the values. There's n words, so there could be at most n unique words. So that's O of n times m. Okay. And then space, we have to create a count for each of the words, right? And each word could be unique, and there's n words, so that's O of n space. So that's the runtime and space of this. If you did it the other way, where you looked at each word and then you looked at the set for each word, you're going to have to look at all n squared pairs. So this would give you another factor of n here. So it's much slower, right? So we've cut down a factor of n by being cute about how we approach this problem. All right, thank you guys. Have a good one.